Chapter 4. Powerplants. Introduction. This chapter covers the engines found on most weight shift control (WSC) aircraft and includes the exhaust, ignition, lubrication, cooling, propeller, gearbox, induction, charging, and fuel systems. Reciprocating engine operating theory is covered for both two-stroke and four-stroke engines. The WSC engine and propeller, often referred to as a powerplant, work in combination to produce thrust. The powerplant propels the aircraft and charges the electrical system that supports WSC operation. End of page 4-1. The powerplant system is composed of the engine, gearbox, and propeller. It is a key component of a WSC aircraft and should be maintained according to both the engine and airframe manufacturer recommendations. Pre-flight information, along with maintenance schedules and procedures, can be found in the Pilot's Operating Handbook, (POH). For special light sport aircraft, SLSA, and/or maintenance references from the manufacturers. Engine inspections and maintenance must be performed and documented in a logbook. A pilot should review this logbook before flying an unfamiliar aircraft. Reciprocating engines. WSC aircraft are designed with reciprocating engines. Figures 4:1-4-3. Two common means of classifying reciprocating engines are they: 1. Number of piston strokes needed to complete a cycle, 2 or 4. 2. Method of cooling, liquid or air. Refer to the Pilot's Handbook of Aeronautical Knowledge for a comprehensive review of how reciprocating four-stroke engines operate. Two-stroke engines. Two-stroke engines are commonly used in WSC aircraft. Two-stroke aviation engines evolved from two-stroke snowmobile and watercraft engines, the difference being that an aircraft engine is optimized for reliability with dual ignition often installed for each cylinder. Two-stroke engines are popular because they have fewer components than four-stroke engines, which makes them less expensive to manufacture and lighter, thus increasing the power-to-weight ratio. Two-stroke engines require that oil be mixed into the fuel to lubricate the engine, instead of being held in a sump and requiring a separate pressurized recirculating system like that of a four-stroke engine. Details on two-stroke oil mixing are covered in the lubrication section. One stroke as the piston moves up is intake and compression, while the second stroke as the piston moves down is power and exhaust. The two-stroke engine performs the same functions as a four-stroke engine in half the number of strokes. End of page 4-2. Figure 4:2. Two-stroke water-cooled engine. Figure 4:3. Four-stroke water and oil-cooled engine. End of page 4-3. A wide range of valve systems are found on two-stroke engines for the purpose of opening and closing ports in the cylinder to let fuel in and exhaust out at the proper time. This is similar to the intake and exhaust valves on a four-stroke engine. One-way pressure valves, called spring, reed, or poppet valves, open when the pressure drops within the crankcase, pulling the fuel from the carburetor into the crankcase. Figure 4:4. Mechanical rotary valves are driven off the engine, rotate to provide an opening at the precise time, and can be on the intake and exhaust ports. Figure 4:5. Piston porting does not use any valves. The fuel inlet port is opened and closed by the piston position as it moves up and down in the cylinder. This is called a piston ported inlet and is used in the two-stroke process description that follows. Two-stroke process. The two-stroke process begins with the fuel entering the engine and concludes as it exits as exhaust. Crankcase vacuum intake stroke, piston moving up. The upward stroke of the piston, figure 4:6a, creates a vacuum in the crankcase and pulls the fuel/air/oil mixture into the crankcase through the intake valve system from the carburetor. Figure 4:6b. This can be a pressure-actuated reed valve, a rotary valve, or a ported inlet system where the lower piston skirt provides an opening for the fuel/air/oil mixture to flow in when the piston is reaching its highest point of top dead center, TDC. At this point, the greatest portion of the fuel/oil/air mixture has filled the crankcase. Figure 4, 6b. Crankcase compression stroke piston moving down. During the downward stroke, the pressure valve is forcibly closed by the increased crankcase pressure, the mechanical rotary valve closes, or the piston closes off the fuel/air-oil mixture intake port is shown. The fuel/oil/air mixture is then compressed in the crankcase during the downward stroke of the piston. Figures 4, 6b to 4-6d. End of page 4 to 4. Crankcase transfer/exhaust piston at lowest. When the piston is near the bottom of its stroke, the transfer port opening from the crankcase to the combustion chamber is exposed, and the high-pressure fuel/air mixture in the crankcase transfers around the piston into the main cylinder. This fresh fuel/oil/air mixture pushes out the exhaust, called scavenging, as the piston is at its lowest point and the exhaust port is open. Some of the fresh fuel/oil/air mixture can escape through the exhaust port, resulting in the higher fuel use of the two-stroke engine. Figure 4, 6d. Cylinder start of compression stroke piston initially moving up. As the piston starts to move up, covering the transfer port, the tuned exhaust bounces a pressure wave at the precise time across the exhaust port to minimize the fuel/air/oil mixture escaping through the exhaust port. Figure 4, 6e. Cylinder compression stroke piston moving up. The piston then rises and compresses the fuel mixture in the combustion chamber. Figure 4, 6e to 4-6f. During this piston compression process, the crankcase vacuum intake process is happening simultaneously, as described earlier. This is why 4 processes can happen in 2 strokes. Figures 4, 6b and 4-6c. Cylinder power stroke initial piston moving down. At the top of the stroke, the spark plug ignites the fuel/oil/air mixture and drives the piston down as the power stroke of the engine. Figures 4, 6f and 4-6g. Cylinder power stroke final piston moving down as the piston passes the exhaust port. The exhaust exits the combustion chamber. As the piston continues down, the transfer port opens and the swirling motion of the fuel/oil/air mixture pushes the exhaust out of the exhaust port. Figures 4, 6h. Piston reverses direction from downstroke to upstroke. As the piston reverses direction from the downstroke to the upstroke, the process is complete. Figures 4, 6h and 4-6a. End of page 4 to 5. Four-stroke engines are very common in most aircraft categories and are becoming more common in WSC aircraft. Figure 4, 7. Four-stroke engines have a number of advantages, including reliability, fuel economy, longer engine life, and higher horsepower ranges. These advantages are countered by a higher acquisition cost, lower power-to-weight ratios, and a higher overall weight. The increased weight and cost are the result of additional components, e.g., camshaft, valves, complex head to house the valve train, incorporated in a four-stroke engine. Exhaust systems. Engine exhaust systems vent the burned combustion gases overboard, reduce engine noise, and, in the case of two-stroke engines, help keep the fresh fuel/oil/air mixture in the cylinders. An exhaust system has exhaust piping attached to the cylinders, as well as a muffler. The exhaust gases are pushed out of the cylinder and through the exhaust pipe system to the atmosphere. Some exhaust systems have an exhaust gas temperature probe. This probe transmits an electric signal to an instrument in front of the pilot. This instrument reads the signal and provides the exhaust gas temperature, EGT, of the gases at the exhaust manifold. This temperature varies with power and with the mixture, ratio of fuel to air entering the cylinders, and is used to make sure the fuel/air mixture is within specifications. When there is a problem with carburation, the EGT gauge will normally be the first notification for a pilot. Figure 4, 8. Two-stroke tuned exhaust systems in two-stroke engines. The exhaust system increases the fuel economy and power of the engine. The two-stroke exhaust system is an integral part of any two-stroke engine design, often controlling peak power output, the torque curve, and even the revolutions per minute (RPM) limit of the engine. The exhaust system must be tuned to produce a back pressure wave at the exhaust port to act as an exhaust valve as shown in Figure 4.6e. When hot spent gases are vented out of the exhaust port, they are moving fast enough to set up a high pressure wave. The momentum of that wave down the exhaust pipe diffuser lowers the pressure behind it. That low pressure is used to help suck out all of the residual, hot, burnt gas from the power stroke and at the same time help pull a fresh fuel/air charge into the cylinder. This is called scavenging and is an important function of a tuned two-stroke exhaust system. Figure 4.6h. End of page 4 to 6. The design of the exhaust converging section causes a returning pressure wave to push the fresh fuel/air charge back into the exhaust port before the cylinder closes off that port. Called pulse charging, it is another important function of the exhaust system. Figure 4.6e. Tuned exhaust systems are typically tuned to a particular RPM range. The more a certain RPM range is emphasized, the less effective the engine will operate at other RPM. Vehicles like motorcycles take advantage of this with the use of transmissions. Motorcycle exhaust pipe builders can optimize a certain RPM range and then the driver shifts gears to stay in that range. Aircraft, with no transmission, do not have this ability. On an aircraft, an exhaust pipe has to be designed to operate over a broad range of RPM from idle to full speed, a reason that simply putting a snowmobile engine on a WSC does not work well. Overall, the two-stroke exhaust system for a WSC aircraft is a specific design and must be matched to the engine to operate properly and obtain the rated power. It also reduces noise and directs the exhaust to an appropriate location. Exhaust silencers can be added to reduce noise, but additional weight, cost, and slight power reduction are the byproducts. Four-stroke engine exhaust systems. Four-stroke engines are not as sensitive as two-stroke engines because they have exhaust valves and, therefore, do not need the precision pulse-tuned exhaust system. However, directing the exhaust out appropriately and reducing the noise are important considerations. Again, using the manufacturer's recommended configurations is required for SLSA and recommended for experimental light sport aircraft, ELSA. Engine warming. Two-stroke engine warming. Two-stroke engines must be warmed because different metals expand at different rates as they are heated. When heating steel and aluminum, the aluminum parts expand faster than the steel parts. This becomes a problem in two different areas of many two-stroke engines. The first place is in the cylinders of the engine. The cylinders have steel walls that expand slowly, compared to aluminum pistons that expand quickly. If an engine is revved too quickly during takeoff before warming up, a lot of heat is generated on top of the piston. This quickly expands the piston, which can then seize in the cylinder. A piston seizure will stop the engine abruptly. The second area of concern is lower in the engine around the crankshaft. This is an area where parts may get too loose with heat, rather than seizing up. Additionally, the crankcase has steel bearings set into the aluminum which need to expand together or the bearings could slip. Many two-stroke engines have steel bearings that normally hug the walls of the aluminum engine case. The crank spins within the donuts of those steel bearings. If the engine heats too quickly, the aluminum case out expands those steel bearings and the crank causes the bearings to start spinning along with it. If those steel bearings start spinning, it can ruin the soft aluminum walls of the case, which is very expensive. If heat is slowly added to an engine, all parts will expand more evenly. This is done through a proper warm-up procedure. Many two-stroke engines are best warmed up by running the engine at a set RPM for a set amount of time. Follow the instructions in the POH, however, a good rule of thumb is to start the engine initially at idle RPM, get it operating smoothly at 2,500 RPM for 2 minutes for initial warm-up, and then warm the engine at 3,000 RPM for 5 minutes. The cylinder head temperature or coolant temperature must be up to the manufacturer's recommended temperatures before takeoff. This may require running the engine at higher RPM to reach required temperatures on some engines. Once the engine is warmed up and the aircraft is flying, it is still possible to cool down the engine too much. This happens when the engine is idled back for an extended period of time. Even though the engine is running, it is not generating as much heat as the cooling system is efficiently dumping engine heat into the atmosphere. An immediate power application with a cooled engine can seize the engine just as if the engine had not been warmed in the first place. In water-cooled engines, on a long descent at idle, the coolant cools until the thermostat closes and the engine is not circulating the radiator fluid through the engine. The engine temperature remains at this thermostat closed temperature while the radiator coolant continues to cool further. If full throttle is applied, the thermostat can open, allowing a blast of coolant into the warm engine. The piston is expanding due to the added heat, and the cylinder is cooling with the cold radiator water, resulting in piston seizure. To prevent this, slowly add power well before getting close to the ground where power is needed. This gives the system a chance to open the thermostat gradually and warm up the radiator water. Just as it takes time for the engine crankcase and bearings to warm up, it also takes those steel parts a long time to cool down. If a pilot lands, refuels, and wants to take off again quickly, there is no need to warm up again for 5 minutes. The lower end of the engine stays warmed up after being shut down for short periods. End of page 4 to 7. Any engine restart is an example in which it would be appropriate to warm the engine up until the gauges reach operating temperatures. The lower end of the engine is warm and now a pilot needs to be concerned only with preventing the pistons from seizing. 4-stroke engine warming. A 4-stroke engine must also be warmed up. The 4-stroke engine has a pressurized oil system that provides more uniform engine temperatures to all of its components. Takeoff power can be applied as soon as the water, cylinder head temperature, CH.4, oil temperatures, and oil pressure are within the manufacturer's recommended tolerances for takeoff power applications. Gearboxes. Gearboxes are used on most WSC reciprocating engines to take the rotational output of an internal combustion engine which is turning at a high RPM and convert it to a slower, and more useful, RPM to turn the propeller. Gearboxes come in different gear ratios depending on the output speed of the engine and the needed propeller turning speeds. Some examples are a 2-stroke RPM reduction from 6,500 engine RPM with a 3.47 to 1 reduction, resulting in 1,873 propeller RPM. A 4-stroke RPM reduction could be from 5,500 engine RPM with a 2.43 to 1 reduction, resulting in 2,263 propeller RPM. A gearbox is a simple device that bolts directly to the engine and, in turn, has the propeller bolted directly to it. A 2-cycle engine gearbox is kept lubricated with its own built-in reservoir of heavy gearbox oil. The reservoir is actually part of the gearbox case itself. The gearbox oil has to be changed periodically since the meshing of the gears will cause them to wear and will deposit steel filings into the oil. If the oil is not changed, the abrasive filings cause even more wear. Some gearboxes have a built-in electric starter motor. When activated, the motor turns the gearing which cranks the engine. 4-stroke propeller reduction gearboxes use oil from the engine oil system for lubrication. Some gearboxes come with a built-in centrifugal clutch and others have allowances for installation. A centrifugal clutch is very useful in a 2-stroke engine because it allows the engine to idle at a lower speed without the load of the propeller. Otherwise, 2-stroke engines can generate a great deal of vibration at low RPM when loaded. As the engine speeds up, the centrifugal clutch engages and smoothly starts the propeller spinning. When the engine is brought back to idle, the clutch disengages and allows the engine to idle smoothly again. The propeller stops when on the ground and windmills when flying. Propeller. The propeller provides the necessary thrust to push the WSC aircraft through the air. The engine power is used to rotate the propeller, which generates thrust very similar to the manner in which a wing produces lift. The amount of thrust produced depends on the airfoil shape, the propeller blade angle of attack (AOA), and the engine RPM. Figure 4.9. Light sport aircraft (LSA) are equipped with either a fixed pitch or a ground adjustable pitch propeller. Fixed pitch propeller. The pitch of the fixed pitch propeller is set by the manufacturer and cannot be changed. Refer to the Pilot's Handbook of Aeronautical Knowledge for basic propeller principles. End of page 4 to 8. Ground adjustable pitch propeller. Adjustable pitch propellers for WSC aircraft can be adjusted only on the ground with hand tools. If an engine is over revving, more pitch can be added to the propeller. If the engine is not developing the full recommended RPM during flight, then some pitch can be taken out of the blades. This should be done according to the WSC aircraft's POH and by a qualified technician. Induction systems. The induction system brings air in from the atmosphere, mixes it with fuel, and delivers the fuel/air mixture, fuel/oil/air mixture for two-stroke engines, to the engine intake and to the cylinders where combustion occurs. Outside air enters the induction system through an air filter on the engine. The air filter inhibits the entry of dust and other foreign objects. Two types of induction systems are used in WSC engines. 1. The carburetor system is most common. It mixes the fuel and air in the carburetor before this mixture enters the engine intake. 2. The fuel injection system injects the fuel into the air just before entry into each cylinder. Carburetor systems. WSC aircraft use float-type carburetors. The float-type carburetor acquires its name from a float that rests on fuel within the carburetor float chamber, commonly known as the fuel bowls. The float maintains the fuel level in the fuel bowls. As fuel is used by the engine, the fuel and float levels drop, opening the valve, letting more fuel into the fuel bowls until the proper level of fuel in the fuel bowls is achieved and the valve is closed. Reference the Pilot's Handbook of Aeronautical Knowledge for basic information on float carburetor operation. Modern 2- and 4-stroke carburetors operate with 3 separate jetting systems depending on engine power. Figure 4.10. When the throttle is closed for engine idling, the throttle valve is closed and the fuel/air mixture is supplied through the idle, pilot, jet and idle, pilot, air passage. The fuel/air mixture is supplied to the cylinders through the bypass hole. Figure 4.11. As the throttle is advanced and the throttle valve is raised, the fuel is sucked up through the main jet but is controlled by the opening and taper of the jet needle and needle jet. This is effective throughout most of the mid-range operation. About half throttle, the main jet size starts to influence the amount of fuel mixed with the air, and this effect continues until it is the main influence at the highest throttle settings. Figures 4.10 and 4.12. End of page 4-9. Two-stroke carburetor jetting for proper mixture. Carburetors are normally set at sea level pressure with the jets and settings determined by the manufacturer. Figure 4.13. However, as altitude increases, the density of air entering the carburetor decreases, while the density of the fuel remains the same. This creates a progressively richer mixture, same fuel but less air, which can result in engine roughness and an appreciable loss of power. The roughness is usually due to spark plug fouling from excessive carbon buildup on the plugs. Carbon buildup occurs because the excessively rich mixture lowers the temperature inside the cylinder, inhibiting complete combustion of the fuel. This condition may occur at high elevation airports and during climbs or cruise flight at high altitudes. To maintain the correct fuel/oil/air mixture, the main jets are usually changed for smaller jets based on the density altitude of the base airport. Operating from low altitude airports and climbing to altitude where the mixture becomes rich for short periods is acceptable. Operating an aircraft at a lower altitude airport with the jets set for higher altitudes will create too lean of a mixture, heat up the engine, and cause the engine to seize. The pilot must be aware of the jetting for the machine to adjust the mixture. Consult your POH for specify C procedures for setting jets at different density altitudes. 4-stroke mixture settings. 4-stroke engines typically have automatic mixture control for higher altitudes or a mixture control that can be operated by the pilot. Carburetor icing. One disadvantage of the carburetor system versus the fuel-injected system is its icing tendency. Carburetor ice occurs due to the effect of fuel vaporization and the decrease in air pressure in the venturi, which causes a sharp temperature drop in the carburetor. If water vapor in the air condenses when the carburetor temperature is at or below freezing, ice may form on internal surfaces of the carburetor, including the throttle valve. Ice generally forms in the vicinity of the venturi throat. This restricts the flow of the fuel/air mixture, fuel/oil/air mixture for two-stroke, and reduces power. If enough ice builds up, the engine may cease to operate. Carburetor ice is most likely to occur when temperatures are below 70 degrees Fahrenheit 21 degrees Celsius and the relative humidity is above 80%. However, due to the sudden cooling that takes place in the carburetor, icing can occur even with temperatures as high as 100 degrees Fahrenheit 38 degrees Celsius and humidity as low as 50%. This temperature drop can be as much as 60 to 70 degrees Fahrenheit. Therefore, at an outside air temperature of 100 degrees Fahrenheit, a temperature drop of 70 degrees Fahrenheit results in an air temperature in the carburetor of 30 degrees Fahrenheit. Figure 4.14. The first indication of carburetor icing is a decrease in engine RPM, which may be followed by engine roughness. Although carburetor ice can occur during any phase of flight, it is particularly dangerous when using reduced power during a descent. Under certain conditions, carburetor ice could build unnoticed until trying to add power. To combat the effects of carburetor ice, some engines have a carburetor heat option. Some of the newer 4-stroke engines have carburetor heat turned on all the time to combat icing. 2-stroke engines are typically less susceptible to icing, but specific installations dictate how susceptible the carburetor is to icing. End of page 4 to 10. Consult the aircraft POH for the probability of carburetor ice for the specific installation and for carburetor ice procedures. Fuel injection induction systems. In a fuel injection system, the fuel is injected either directly into the cylinders or just ahead of the intake valve. A fuel injection system usually incorporates these basic components: engine-driven fuel pump, fuel/air control unit, fuel manifold, fuel distributor, discharge nozzles, auxiliary fuel pump, and fuel pressure/flow indicators. Figure 4.15. The engine-driven fuel pump provides fuel under pressure from the fuel tank to the fuel/air control unit. This control unit, which essentially replaces the carburetor, meters the fuel and sends it to the fuel manifold valve at a rate controlled by the throttle. After reaching the fuel manifold valve, the fuel is distributed to the individual fuel discharge nozzles. The discharge nozzles, which are located in each cylinder head, inject the fuel/air mixture at the precise time for each cylinder directly into each cylinder intake port. Some of the advantages of fuel injection are: 1. No carburetor icing. 2. Better fuel flow. 3. Faster throttle response. 4. Precise control of mixture. 5. Better fuel distribution. 6. Easier cold weather starts. Disadvantages include: 1. Difficulty in starting a hot engine. 2. Vapor locks during ground operations on hot days. 3. Problems associated with restarting an engine that quits because of fuel starvation. End of page 4 to 11. Ignition system. The typical ignition system on WSC aircraft provides the spark that ignites the fuel/air mixture in the cylinders and is made up of magneto/generators, control boxes, spark plugs, high-voltage leads, and the ignition switch. For most LSA engines designed specifically for aircraft, a magneto/generator uses a permanent magnet to generate an electric current independent of the aircraft's electrical system, which might include a battery. The aircraft electrical system can fail, the battery can go dead. However, this has no effect on the ignition system. The electricity from the ignition magneto/generator goes into the ignition control box where the correct voltage is produced in time to fire the spark plugs at the proper time. Modern WSC aircraft use an electronic capacitance discharge system that operates without any moving parts to increase reliability and efficiency. Capacitance digital systems, CDI, operate similarly, but they have the ability to change the timing of the spark for different RPM. Consult the POH for the particular system for each engine. The system begins to fire when the starter is engaged and the crankshaft begins to turn. It continues to operate whenever the crankshaft is rotating. Most WSC aircraft incorporate a dual ignition system with 2 individual magneto/generators, separate sets of wires, separate sets of control boxes, and separate sets of spark plugs to increase reliability of the ignition system. Each magneto/generator operates independently to fire one of the 2 spark plugs in each cylinder. If one of the systems fails, the other is unaffected. The engine will continue to operate normally, although a slight decrease in engine power can be expected. The operation of the magneto/generator output to the ignition system is controlled in the flight deck by the ignition switch. Since there are two individual ignition systems, there are normally two separate ignition toggle switches or separate positions on the ignition control, as shown in Figure 4.16. Identification of a malfunctioning ignition system during the pre-takeoff check is observed by the decrease in RPM that occurs when first turning off one ignition switch, turning it back on, and then turning off the other. A noticeable decrease in engine RPM is normal during this check. If the engine stops running when switching to one ignition system, or if the RPM drop exceeds the allowable limit, do not fly until the problem is corrected. The cause could be foul plugs, broken or shorted wires between the magneto/generator and spark plugs, or improperly timed firing of the plugs because of a defective control box. It should be noted that no drop in RPM is not normal, and in that instance, the aircraft should not be flown. Following engine shutdown, keep the ignition switches in the OFF position. Even with the battery and master switches off, the engine can fire and turn over if an ignition switch is left on and the propeller is moved because the magneto/generator requires no outside source of electrical power. The potential for serious injury in this situation is obvious. Standard category aircraft engine systems are described in the Pilot's Handbook of Aeronautical Knowledge. However, these engines are not typically used on WSC. Automobile engines or other non-aircraft engines may be used on WSC where the ignition system runs off the battery rather than a magneto/generator system. In this case, if the battery system fails, the engine ignition system will fail and the engine will stop. Combustion. During normal combustion, the fuel/air mixture burns in a very controlled and predictable manner. Although the process occurs in a fraction of a second, the mixture actually begins to burn at the point where it is ignited by the spark plugs, then burns away from the plugs until it is consumed completely. This type of combustion causes a smooth buildup of temperature and pressure and ensures that the expanding gases deliver the maximum force to the piston at exactly the right time in the power stroke. Detonation is an uncontrolled, explosive ignition of the fuel/air mixture within the cylinder's combustion chamber. It causes excessive temperatures and pressures which, if not corrected, can quickly lead to failure of the piston, cylinder, or valves. End of page 4 to 12.